to satisfy the global CI. Okay. So now you have so the conditional independencies are simple. And the good news is that when your distribution is positive, in the sense that for all combination of variables, you will have a positive probability, that for no combination of variables is impossible. Nothing has a probability of 0. If you have such a distribution, then these three rules are equivalent. Okay? So the proof of that I will not go into, it's somewhat involved. But the interesting thing is the relationship between conditional independencies and factorization. Now again, we have a bad news for the case of MRFs. For the case of Bayesian networks, there was a very simple way to prove that the local conditional independencies imply the factorization of a joint distribution in terms of potentials. For the case of conditional independencies, we have a theorem, but the proof of that theorem is complicated, and this is not something that I can cover in a tutorial like this. So the theorem, this is called Hammersley-Clifford theorem. It says that if a distribution is positive, and if it conforms to if you have a distribution which satisfies the pairwise conditional independencies of a graph G, then it can surely be factorized in terms of the potentials which go over the cliques of the graph. You don't need to consider any potential over variable subset which are larger than a clique. So just this is sufficient to factorize the distribution. Okay? So this is the theorem which sort of expresses the relationship between conditional independencies, graph structure and factorization. Okay? So we are not going over the proof of this one. So now, as I mentioned earlier already, for undirected graphical models, there are several applications in physics, say for modeling molecular structures, in vision for the image understanding. Another very popular undirected graphical model is a conditional random field which is used for information extraction. Very often the social networks are represented as undirected graphical models, and several other applications exist for undirected graphical models. Okay.
I have a question.
So here is a comparison of directed and undirected graphs. So first, the fact is that both MRFs and Bayesian networks are not complete in the sense that there exists distribution which cannot be represented by either of them. They are not. Hello.
My question is, for the Bayesian network, you have defined the potentials for individual vertices, whereas for the Markov random field, you have defined it over all possible cliques in the graph. So, so what is the motivation behind it? Because of that last theorem, that from the individual potentials of the cliques you can compute the thing. That's why it is defined that way, or what is the motivation?
Yeah, that is the motivation. But let me answer it. Do you have any other questions?
No.
Yes.
Okay, let me answer it. Okay, so a very relevant question about why is the way we define the potentials different for Bayesian networks and for MRFs. So first let me say that for Bayesian networks, the potentials are not only over single variables. It's single variables and its parents. So the potentials involve several variables, even for the case of a Bayesian network. It's just that the potential represents the conditional probability of that variable given its parents. But if you consider the argument of the function or the number of parameters used to describe the potential, it is exponential in the size of the parents. Okay, so if a variable has k parents and each parent can take two possible values, then you will need 2 to the power k parameters to describe this potential. Okay? Whereas in the case of undirected graphical model, the potentials are defined over if you try to define the potentials through something other than clique, then find that suppose if you have potentials defined over, I mean it's not always the case, but suppose if you have potentials, so actually there are two things. So when you have potential, so we are trying to understand the relationship between graph structure and the factorization of a distribution. If you have a potential, if you have a factorization of a distribution involving a subset of variables, then those subset of variables have to be a clique in the graph. This one-way relationship has to hold in the sense that if there are two variables which appear together in any potential in the factorization, there has to be an edge between them in the graph. Because otherwise, in the potential, you can make these two variables correlated or directly dependent on each other. The graph structure will therefore not faithfully represent this correlation. It will say that there exists some combination of variables which will be independent, which your potential may not enforce. Okay. Now the second way, which is to say that every clique there has to be a potential. This is actually not a strict rule. It just says that you are allowed to have a potential corresponding to a clique in the graph, but you could choose to define the potentials over subsets of cliques also. Okay. Did I answer your question?
So actually,
and if you try to do something else, like for example, try to define potential over a variable and its neighbors, like the way we did for Bayesian networks, you will find that it is not very simple. Okay. Hello.
So actually, so the question is now you are defining this for all possible cliques in the graph, right? So now there
Yes.
There can be exponentially many cliques. So and then you have to define this probability for this exponentially many possible cliques. So will it not be very computationally intensive?
Oh, okay. So the question. So the question is, in a graph you can have an exponential number of cliques. Okay, so won't it be computationally very expensive? So the answer is that you can, when you define the potentials, you can choose to define the potentials only over a subset of the cliques. For example, you could choose to define the potentials only over the maximal cliques in a graph. Okay, and the maximal cliques will not be exponential. Okay. Finding the maximal clique is difficult, but for the case of special graph structure that we will be considering, which is basically triangulated graphs, finding the maximal cliques is also not difficult. Okay, so you can always choose. For example, if I have a completely connected graph, I might still choose to define the potentials only over the edges of the graph. That is in fact very, very common. A very popular kind of undirected graphical model is what is called as a pairwise graphical model. So in a pairwise graphical model, like you might have a fully connected graph, but you will define the potentials only over the edges in the graph. But because you have a potential over every pair of variables, because of the rule that I mentioned earlier, that if you have a potential over a subset of variables, they have to be a clique in the graph. Because of that, if you have an edge over every pair of variables, the MRF corresponding to that will be a complete graph. But the potential does not have to be over all the variables as a single potential function. Okay.
Okay, then we can move on.
I assumed that answered the question.
Yes. That part
Okay.
answered.
So the phone is not ringing. So I'm going to proceed forward. So we are talking about the difference between directed and undirected graphical models. So there are, I was mentioning, some distributions which can only be represented with a Bayesian network, but which cannot be represented as an MRF. So this is a very simple example of such a distribution. Say I have three variables, call them x3, x4 and x5. And x5 has tails x3 and x4. Now, if you look at this graph structure, what it tells us is that x3 and x4 are actually independent of each other. If you apply the local conditional dependencies rule, you know that x3 and x5 are independent of each other because x3 is a non-descendant of x4 and x4 has no parents. So x3 is independent of x4. But if you know x5, then x3 and x4 become dependent on each other. This is basically the common outcome kind of a situation. Suppose there is a nice application for it. So suppose you have you see a particular trait in a puppy. So you find that the puppy has brown eyes, okay, and normally the mother dog and the father dog, the eye color of the dogs might be totally independent of each other. And so if you know the eye color of the dad dog, that will not tell you anything about the eye color of the mother dog. But suppose if you see the puppy dog you see has brown eyes, and the dad dog does not have brown eyes. So the moment you see that the dad dog does not have brown eyes, then you can update your expectation of the eye color of the mother dog. It's very likely that the mother dog will have brown eyes. So this is a situation where the information about x4 and x5 combined is giving us some information about x3, and therefore we can claim that x3 is not independent of x4 given x5. Now, such kind of conditional independencies cannot be expressed in an undirected graphical model. In an undirected graphical model, because of the global CI rule, which says that if a subset of variables separate two other subsets, then they will be conditionally independent given that first subset. Because of that, if two sets of variables are separated, then increasing the removed variable set will only keep them more separated. So this non-monotonicity does not hold, and so therefore you cannot represent such distributions in RFs. Similarly, here is an example of a distribution which is a symmetric relationship which says that x2 and x5 are independent of each other given x3 and x4, and x3 and x4 are independent of each other given x2 and x5. This also cannot be represented as a Bayesian network. Okay, so you can try it out and you will find that you cannot draw a Bayesian network which is a acyclic graph and which expresses only these two conditional independencies and nothing more. Okay, so the other things about the potentials and the dependent structures we have already discussed. Now, and sort of a natural question is, when should I use a Bayesian network and when should I use a undirected graphical model? Well, actually, it depends on what kind of data you have and how you will be drawing the graph. So actually, if you are trying to draw the graph yourself and you will be assigning the potentials yourself manually, then you might be better off using a Bayesian network, because then you can capture the potentials in intuitive ways. You can just use your domain knowledge to define the potentials. Whereas if you have potentials, which are sort of defined in terms of features as in typical text mining applications, then you might be better off using an undirected graphical model. And in general, it does not matter much which of these two graph structures you are using. Okay. So now we'll go to the next major topic, which is answering inference queries on the distribution. Okay, so actually we have very little time left, and we also have to cover structured learning. So this portion on inference queries, I will have to go a bit fast so that we can go to structured learning, which is also a very important topic. And this material that I am covering here is textbook material, and there are very good books for you to read from. I have mentioned the names of the book at the end of the slide. So I am just going to kind of cover inference, which is a very interesting and very exciting, but it's a very, very detailed topic. It can, I usually when I teach this topic in class, I take around 10 classes to cover inference, and I will cover this in 10 minutes here, and then we will go to structured learning. So inference, we are going to be interested in two kinds of inference queries. The first is the marginal probability queries, where you are given as input a small subset of variables, typically just one variable, and you are interested in calculating its marginal probability from the joint distribution that the graphical model expresses. So in the Bayesian network about people, you might be interested in finding the probability of someone having high income and degree equal to PhD. Here we are interested in this two variable marginal probability. Or say in the image application where you have this undirected graphical model, you are interested in, say you have picked one pixel, say pixel Y9, and you want to know what is the probability that it is part of the foreground. So if you want to answer these queries directly just by summing up or marginalizing over all the variables which are not in the query set. So if you want to find probability of x1, you sum up over all the remaining variables, x2 through xn. This is how we know how to compute marginal probabilities. But if you do this explicitly, then it's going to be computationally very intractable and you don't want to do it. Okay. The second kind of queries, this is the mode queries, where you want to find the assignment of labels to variables for which the probability is maximized. So this has applications in typical sort of text prediction kind of models. Like say you want to find the most likely set of labels of nodes in a social network, or you want to find the most likely entity labels of words in a sentence. So here you are interested in marginalizing the distribution through the max operation instead of operator instead of the sum operator. That's the only difference. So here, for example, you want to find the max over x1 through xn, and the argument of this max will give you the answer that you're after, which is the assignment of labels or values to variables for which the probability is maximum. This is also the mode of the distribution. So these are the two very popular kind of inference queries. So as I mentioned, that if you try to do it explicitly, then it's going to be intractable. So what we want to do is to use the graph structure to simplify the summation. Okay? So we will illustrate the simplification, the main idea of the simplification using this very, very simple graph. So you have this very simple graphical model. Let's say you have a graph over 5 variables. And this is a Bayesian network, and you have this chain which expresses the dependency among these 5 variables. So it is like a part of a hidden Markov model. And let's say you are interested in finding what is the probability that variable y5 takes value 1. Okay, so if you have to do it through the explicit method, then in order to find what is the probability that y5 is equal to 1, you have to sum over all the remaining variables y1 through y4 in this joint probability distribution over y1 to y4 with y5 fixed to a value of 1. So doing this explicitly is not an option. So what we want to do is exploit the factorization of the distribution to do this summation efficiently. So we'll see how we will do it in this chain case. So because our graph is a chain, we will have potentials only over adjacent variables. So in that chain there, let's say we have potentials over the adjacent variables y1, y2, and then another over y2, y3, and third one over y3, y4, and the fourth one over y4, and variable y5 taking just a fixed value. So the explicit method will first multiply together these four potential functions, which will give rise to you a table with four variables. The other one is fixed. So it's a 4-dimensional table, which is actually of size exponential in the number of variables. And then you will remove one variable at a time from this 4-dimensional table, which is inefficient. Now we can just apply high school algebraic ideas and push some of the summations inside the product. So we find that y4 does not appear in these two potentials. So we can do this summation before we do this multiplication. Okay, so we push y4 across these two multiplications and we do this summation over here. So first we compute the product of these two potentials. That will still give us just a two-dimensional potential table. And then we will do this summation over y5, y4. Okay, so we do this. So we compute this product, do the summation, and we say the result we are going to denote as this singleton function, single variable function. Let's call this b3, y3. Because it is only over variable y3. y4 has been eliminated. So the only surviving variable here is y3. So now this factor will multiply with the potential that existed in the graph. This will again be a intermediate result involving just variable y2 and y3. And from there we will eliminate variable y3. And now the result will be only in terms of variable y2. We'll do this multiplication, eliminate variable y2, and now we will just do the summation over variable y1 and we get the result. So this is the main idea about efficiency of inference in graphical models. The main idea is to do the computation in such a way so as to exploit the factorization of the probability distribution, to push the summations or maximization when you are answering the map queries and do the computations differently. Now there are many efficient algorithms for doing this efficiently. There is so actually there are alternative kind of queries. Sorry, I will have to. Oops, I don't know. Just 1 second, please. I pressed the wrong key. So I'm going to skip this part, okay, here, and okay. So for example, in HMMs, the same computation arises, same kind of computation arises when you try to find the most likely states in a HMM. So that can also be solved by pushing the maximization within the product. And in fact, that is the famous Viterbi algorithm. Now, in general, for arbitrary graphs also, you can use this idea. There is a famous algorithm called variable elimination algorithm, which can be used to make computation efficient. I am explaining that through an example here, but I will have to skip it now because I would like to cover structured learning now. And then there is this very famous method based on junction trees. So again, you can find it in well-known textbooks on graphical models. So the junction tree algorithm, just let me leave with this one note. It is an optimal general purpose algorithm for exactly computing the marginal probability, the answers to marginal and map queries in a graphical model. So it is optimal in the sense that you cannot do any more, you cannot do any better than it, but for general purpose graphs. If you have some special graph structure, then you might be able to exploit that to design some specialized, more efficient computations. But in general, the junction tree algorithm for arbitrary potentials is optimal. So, you know, here I was earlier sort of planning to cover the junction tree algorithm with examples, but now I will skip that. And this is actually a very interesting topic, and for people who are interested in graphical models, I encourage you to read up about it. There are many implementations available for you know, graphical model inference, but you know, junction trees, it's optimal for getting the exact answers. Many real-life graphical models give rise to very large junction trees, and then there is interest in designing approximate inference algorithms for such graphical models. And a major research area in the graphical model community is designing such approximate inference algorithms. You might have heard names like belief propagation, and sampling, git sampling. These are sort of tools which are available for approximate inference. Then there is this topic of how you construct the graph structure in a graphical model and how do you learn the parameters. And again, I will have to skip it because we have just 20 minutes left to talk about structured learning. So now I'm going to go to structured learning. So unless there are some quick questions on graphical models, I'm going to now start with structured learning. Okay, so in structured learning, this is actually a very powerful tool in the sense that it will allow you to model several text mining applications in ways which give you the advantage of SVM kind of accuracy, but which give you the flexibility of graphical models and more, in the sense that you can use the structured learning model to solve problems where the predicted output is a structure. So this is illustrated with a difference with existing. So suppose if you try to use a simple classifier, like say an ACM or a logistic classifier or a decision tree model, then you give as input an X and the output class variable is just a scalar. But in structured prediction, your output label can be a structure. I mean, that is why the name structured learning. So the output is a structure, and in the simple case, the structure could just be a vector of labels, like in the case of graphical models, the output is a vector of labels. But in general, it could be anything like a segmentation or a parse tree or an alignment. You will be seeing examples of that. So the output space, this makes the output space very large. Okay, so it could even be exponential in the size of the input for some definition of the input size. Okay, and so how do you actually even define a learning problem in such a domain? So the main idea in structured learning is that you first have to define a feature vector which works jointly on the input X and the output Y. And this feature vector is of fixed size. And the structured model essentially assigns parameters corresponding to this set of K fixed size features that you have. Okay? So we'll be seeing examples of that. At this moment, I understand that this is all very abstract. But once you have defined this feature function, now you can associate the score for any prediction Y that you want to make with an input X. Okay? So let's use this notation S X comma Y to denote the score that is assigned when an input X is associated with an output Y. Recall that Y is some complicated beast. It could be any arbitrary structure. But we make it tractable through this feature function that we have defined over coupling input X and Y. And then corresponding to this K feature function, we have these K parameters, and this way we define a score over X and Y, which is just the dot product of these parameters with the feature vector. So W is a vector of length K, capital F is a vector of length K, and that gives you this single scalar score, coupling X and Y. Once you have a score, now you can define your prediction problem, solve your prediction problem as that of finding a Y star for which the score is maximized. Now, in general, of course, when we are talking about outputting Ys, which can be just about anything, the space of possible Ys will be exponentially large in the input size. So we need some method of solving this argmax problem efficiently. So what you have to do when you define a structured learning problem is to define your feature function in such a way that the feature function decomposes over various parts of Y. So instead of thinking of Y as some arbitrary black box unit, you assume that the feature function has smaller parts. And all throughout this part, I am going to use this notation C to denote the different parts of Y. So this is also in line with the notation that we used in graphical models for C to denote clicks over smaller sets of variables. So suppose when Y is a vector, then YC denotes a subset of all possible n variables, and so that is like a click in the graphical model connotation. And so you have a feature vector which sums over the different parts of Y, and because of this decomposition of the feature function, because the feature function is not this monolithic thing, but rather it decomposes over smaller parts of Y, you can use standard ideas from dynamic programming to solve this argmax problem efficiently. Okay, so in order to use therefore the framework of structured learning, you have to identify your space of possible Y's, and you have to define the feature function, and you have to make sure that the feature function decomposes, so that then you can use ideas from dynamic programming to solve this argmax problem efficiently. Now we come to the learning problem. So when, unfortunately, because of lack of time, we could not cover learning for the case of graphical models. For structured learning, learning is the main topic. So for the training problem, our goal is to find a W, which is like training a classifier model, it's equivalent to that, where we are given as training data several correct input-output pairs. So we are going to denote this input-output, correct input-output labeled data pairs as X1, Y1. So note that these are all vectors, and therefore they are represented as bold-faced alphabets. Okay. So I'll just quickly go over some applications of structured learning, and then we'll go into the training algorithm. So for structured learning, one very popular application is in information extraction. So suppose in information extraction, I'm assuming you have heard about it a lot already.